We will try to get through regression this week nonetheless. And we will definitely get you what you need to know for this week's lab. Right. We had already introduced this idea that if you want to model your world state versus your data, right, that you'll set up some kind of relationship where you say the probability of A given the probability of B and some parameters theta, and we'll model this as some distribution on A which takes a function of B and theta. So we'll be doing that today, again with regression. We've seen one example of regression where we solved it using, well, we didn't really solve it. We said one could solve it using maximum a posteriori. So this week we're talking about regression, and we're going to start off with maximum likelihood regression, and today we'll do the Bayesian form as well, and we'll leave nonlinear, probably leave nonlinear for Thursday. All right, so there's a slight missync because these are the old slides. You're holding new slides, and so I'm going to try to point out a few places where we can improve those. Our example we've seen before is this one where we say, okay, I've got images coming to me as a sequence, but I'll just look at each frame independently. I'll extract 100 pieces of information from this, so I'll have a 100-dimensional X vector. And this particular case, they were trying to estimate the pose of a human, so they said, okay, we have a number of joint angles. We will have, in this case, 55-dimensional output. So we'll want W to be a 55-dimensional vector telling us what are the joint angles at all the different joints in the human body. For our purposes, you could think of something slightly simpler. We'll be working today with a W that is only one-dimensional. So you might say, okay, maybe I'm going to have the same 100-dimensional input X, but my one dimension that I'm trying to estimate, is the velocity with which the person is walking, right? Positive or negative, and it's some floating point number. I visited the BBC this summer, and they were telling us about how they have this computer vision system that they use at the swimming pools when people are diving, when athletes are diving. They point it at the water to measure the splash, right? So they measure a number of things. Can you guess what the most important part of their X vector is when they're trying to measure the splash?
The height of the splash.
The height. I thought so too. No, it's the number of white pixels. So in their X vector, the number of white pixels is part of their X vector, and their output is simply sort of a splash-o-meter value from sort of 0 to super, cannonball kind of splash. Okay, so whatever example suits you, for now let's just consider that we want a one-dimensional output. We're going to use a discriminative model for this. Maybe we don't need to necessarily explain this too much, right? We'll just say, all right, well, just remember we're putting the W here, we're putting the X vector here. I'm doing this without being a vector. And so we're going to need some function that's a function of the input data, because our distribution will be on the world state. Okay. Typically, if we have a nice continuous single-dimensional variable like our world state is here, we might say, okay, well, I'm going to use a normal distribution to model that. That does a pretty good job and has some pretty nice behavior. So this is, to some extent, repetition of what we've seen before. We say, all right, I want to know the probability of the world state for some training example I, given that I have the input data, the 100-dimensional vector here, and some parameters. And that's going to be a normal distribution on the world state, where I have some function of x for the mean, and the variance here will keep it fixed. So this is keeping things very simple. We'll try to come back to this for a brief word later, but for now we're keeping this model fairly simple and saying, look, there's just this linear relationship between the inputs and sort of what the outputs are doing. The output's going to be this Gaussian function, this Gaussian distribution on top of this linear function. This linear function, right, it's linear, we're just doing a simple multiplication times our data x. If I don't remember, please ask me later about sort of the pros and cons of doing regression with more dimensions, right? For now, we're just worried about a single dimensional W. All right, so our setup is going to look like this. We're going to get a bunch of training examples, these blue dots. We know that we're sort of making some choices here. One of our choices is we're going to use a Gaussian distribution for our world state. So our probability of world is this Gaussian function, and we're going to have to figure out the mean and the variance. When we do this, if we're successful, we're going to have this sort of linear relationship between the input, the x, and the output w. And we know that we have that profile, that sort of normal distribution profile on each of the slices. So this is sort of a nice setup, but we're going to try to simplify the notation, and then we're going to use that notation throughout the rest of this week. We said, well, we got this linear relationship. If we look at, let me go back here, we've already discussed this, right? Phi 0 is the y-intercept, and phi 1 is the slope, the rise over the run, delta y over delta x. So can we simplify the notation a bit? Well, instead of having it sort of written out like this, phi 0 plus this vector, which in this case is what's the dimension of the bold phi right now? What is it?
The same as x.
The same as x. Good answer. What's the dimension of x?
100.
100 by 1, we said, right? So, all right. So if we augment things a little bit, if we augment this 100-dimensional vector by adding it, by appending a 1 in front of it, or prepending a 1 in front of it, and we call that sort of our new, this is a bit of abusive notation, but we'll sort of redefine bold x to be a 101-dimensional vector, where we always put a 1 in the first slot, and then we put the rest of the data in the rest of the slots. Then we can do the same thing for our bold phi. We redefine bold phi to be phi 0 followed by these other phi's. And if you're trying to work this out, right, we said that an x vector is 100. Erase this. We've got this down now, right? So an x vector is 100 this way and sort of 1 this way. So all we're doing is we're saying, okay, take this column vector, rotate it so it's a row. So now we have this long row, and then we transpose it back down so it's back to being a column vector. So nothing too fancy, but we're keeping ourselves sort of honest in terms of the orientation and the dimensions. And that'll be handy, I think, to keep track of what's going on with our variables. All right. So now we've got 101 by 1 dimensional x, 101 by 1 dimensional phi, and so our new model for probability of the world state given our data and our parameters is still the same, normal distribution on W, except we've simplified this equation into this, and it's just a slight renaming of the variables. Is that okay? In MATLAB, you could have prepend a 1 and you're good to go. We'll be doing this a few times, so sort of keep track maybe of the fact that when we now have this nice multiplication, it's hiding this little 1. All right. So if we had been talking about a single individual pair of training data, an example input and an example output, if we consider that we are still treating our data as being independent, in other words, I have I examples, it doesn't matter in which order I pulled the I's out of my world, right, and showed them to you and said, here's an example input, here's an example output. Then it's possible to use this kind of notation to express not just one training pair, but all of them all at once. So we'll say, all right, instead of having little bold x, we're going to make this collection of I times, this is D, right? So this is, we said 100 dimensional, right? So we have D times I, this is our new, so this is x1, x2, and this is capital X. Well, nothing complicated, right? We've just appended all our data together into a single big matrix. All right. Bold phi didn't depend on I in the first place. It was just d-dimensional, so 100 dimensional or 101 dimensional when we did the prepending, and it stays the same size. The only thing that may be slightly tricky is that, remember we had a constant variance, we said. Constant variance, just a single number, we used that was the variance for this normal distribution regardless of which subscript I we had. And so in order to be compatible with this here, what's the dimension of this? I haven't worked it out. Yeah? X is, so X by itself is what dimension?
D by I.
D by I. So with the transpose it's I by D. So this has to be D by 1. So the product is it should be I by 1. Yes, that's right. Yes, that's right. So we have I by 1, and so we need I variances. Well, in fact, because this is all done as a matrix, this is simply an identity matrix. So this I is not the same as as non-bold capital I. Yes? Can we agree on that? So this I is the number of training examples we have, but the identity matrix I bold, which lives in a completely different world from that. I bold is the identity matrix. Looks like this, has a bunch of 1s, right? And so if you pre-multiply it by a scalar value, you just get a bunch of sigma squareds for your new covariance matrix. Is that okay? Yeah? All right. So if we can promise to keep in mind this identity matrix multiplied by a scalar, I'll erase it so we don't get confused with our capital I, our number of training examples that we have, training pairs. All right. So at this point, we have the setup and we're ready to start learning. So let me set up the problem a little bit so that we don't get confused between posteriors and likelihoods. It's very easy to get confused, and that's not the point to confuse you. The point is to say keep track of sort of what your objective is. So back to sort of very basic Bayes rule. We're saying that we have the probability of our parameters jointly with our world data. Let me make this bold so that it's consistent with the notation we have here. And so really we kind of care about this joint probability. But we really want to know when we're learning what are these parameters. Of course, we're given some training inputs. And so we can now separate this off into two conditional probabilities that are equal to each other because Well, because we can equivalently say, all right, let's isolate probability of theta. Can you guys see this? Okay, so I'm going to do probability of theta. I'm going to write something like this on the left side, and write something like this on the right side. And I'm going from here. So, probability of theta given what? You have to speak up. W and X. I can put those in. Times probability of W given X. Okay, so that's me isolating the theta. I had a joint probability on theta in the world, and we've isolated, very good, we've isolated our theta here, and we keep track of everything else. Okay, I could have easily done the other variable that I have joint probability over, so let's do that. So what is it?
We're going to W given theta X.
Times
Probability of theta given X.
Okay. The thing I'll add is that frequently you'll see this, and maybe this is us being sloppy. Frequently, people will just write this as probability of theta because they say, well, sometimes my prior on theta comes by looking at the data, looking at the training examples. Sometimes it comes by some other source of external knowledge, and so they don't always write it as probability of theta given X. I think it's probably more elegant to keep it this way, but you'll see in the notes in the book sometimes it's going to just appear as probability of theta. Okay, so I'm not trying to dazzle you here, but we're going to refer back to this as we go forward. So, I've given you training examples, W's and X's. What's your goal now at learning?
Find theta.
Find theta. You want to fit your model parameters to the training examples you have. To find theta, you're going to try to maximize the overall probability of your W given X and theta if you're doing maximum likelihood. So, well, how does that work? So if we're saying I want to know the best theta, then probability of W, so let's say, do it this way. I want to get the best theta. So I could move this term into the denominator here, right? So probability of theta given W and X equals this divided by this denominator. And then the likelihood term, this one here, this term here becomes the likelihood then, right? Equally, if I were solving for probability of W given theta, so the condition we'll be doing at inference, I would move this over to the other side, to the denominator on the other side, and then something else would be the likelihood. So if I'm going to use the maximum likelihood approach and estimating the best theta, this term here becomes the one that I'm computing the likelihood for. And we know that if we want to find the theta that maximizes this probability, that's equivalent to finding the maximum, the theta that maximizes the log likelihood, right? Log likelihood, the log is monotonic, so it's okay to take the log. The log is nice because we happen to be dealing with the normal distribution. So when we take the log of our Gaussian, we get this separation of terms, right? Because we've got products in the equation for the Gaussian. And now we say, great, take the derivative of this, set it equal to 0, and solve for your variables. And in this case, it's easier to start by solving for your phi hat, because then it through linear algebra, right, we end up just transforming these terms into this. We didn't need to worry about the sigma squared, the 2 pi. Well, there's no variable there anyway, so we're just focused on this last term, and it's the numerator, in fact. So we now have a closed form solution for our vector of weights, our phi vector. Right? This is the maximum likelihood solution for it. And once you have that, in a similar way, you can solve for sigma hat squared, right? And this is the closed form solution for that. If you look at sigma hat squared, you might recognize some shape to it here. We're taking the x vector times the already computed weights there for our phi, and we're subtracting them off from the world state. Basically, we're saying I have a vector of outputs. Given this just computed phi, how different is what I'm computing from the desired outputs, right? So how much deviation is there from what I know to be the training outputs? And so squared and normalized by the number of training examples we have. So that's it. That is maximum likelihood linear regression. Linear because our function of x is linear. Maximum likelihood because we said, all right, to find the best theta, let's just focus on this. What did we ignore? Prior. And we also kind of went greedy. We just picked a single point in the space of possible thetas. So it works. This is the result you've already seen. The things to note about it. While we are, let's say, happy with the result we have, we're going to have a fixed this y-intercept here. And if we change the slope, let's say our accuracy in estimating the slope was a little off, then the interesting that will happen is we might still get these points right because they're close to the y-axis. But what happens when you have a very long stick and you change the angle just a little bit, right? The point far away moves quite a lot. So it's possible that suddenly, with a little bit of change, maybe we move one of these data points a bit, this whole line will move vast distances out here. The further away you are from the y-axis, the greater the impact of our estimates of slope. When there were, as we said, I think in chapter 6, we've already mentioned the fact that, well, this is where the data points are. We should be more confident where the data is, sort of less so elsewhere. Another limitation is that we don't have the flexibility to fit anything more complex. Out of the gate, we said, let's do linear regression, fit a straight line to this data. Is this data a straight line? Is it a linear relationship between input and output? If it is, it's a very, very noisy set of data, and maybe we want the ability to have something more complex in there. I've already erased that thing where we plug in our own equation, right? But you can already probably think ahead and say, well, maybe we don't have to have a linear equation in there. Maybe we can do something more creative. All right, so that's where we're going to go. We're going to go in sort of short order. The first one we're going to do is Bayesian formulation. This was our maximum likelihood linear regression. We're still going to do linear regression, but we're going to do the Bayesian form to address this problem of being overconfident far away from the points where we shouldn't be so confident. So we'll do that today. On Thursday we'll do linear. We'll move from the linear model to the nonlinear model, and that will allow us to fit more complicated sets of points. And we will talk about how to deal with how to introduce a sparse prior where the problem you've just seen is based on saying I have a long x vector, and I'm going to make some function, some linear function of x, and that's how I'll calculate w. but what if I have a long x vector, my 100-dimensional x vector of the human, and all I'm trying to do is estimate the tilt of the head on that person. So I have a lot of other parts of that x vector that are bogus, right? And we're trying very hard to accumulate enough training data to fit those parameters, to figure out what the phi's are that should be multiplied by all those bogus parameters that will still give me an accurate tilt angle for the head. In other words, we might be working too hard with too many variables to estimate something that's actually quite simple. And so that's where the sparse prior will come in. Right. So let's do the Bayesian formulation. It's not going to be, it shouldn't be shocking compared to what you've seen already with the maximum likelihood version. But the difference is we're going to keep track of our uncertainty of what? Theta, the parameters. We're going to say, well, instead of just picking one theta hat, picking one theta, putting a hat on it, saying you're special, we're going to keep track of all of the parameters. All right. So we said, all right, we can, and this is, yeah. So this is where, if you, in the notes, you could change this probability of W given X. You probably want it to be this, right? So we're in fact, I mean, you could probably tell from the equation, right, that obviously we're dependent on theta, yes, but our likelihood term, more strictly speaking, is probability of W given theta and X. Okay, so if you want to update your notes. And apologies for the technical difficulty there. All right, so we've got that model from last time. The linear regression part of it can still be modeled the same way. Only now we're going to add in this prior on theta. Theta includes, so theta encompasses. Let's write it up here. Yes, theta includes our phi's and our sigmas, but we're going to persist in keeping a fixed sigma squared as our variance because it will be simpler that way, and we don't necessarily we have a solution for it that I'll come back to. Our prior is a Gaussian distribution on the parameter, the part of theta that we care about. So it's the phi vector. This is a vector, right? And we're going to say, well, we don't have a lot of information about the parameters. We'll just assume that these numbers are small, so they're centered at 0 with some variance. And so that will again be the identity matrix multiplied by some scalar. In this case, the scalar, we're saying, well, this was the sigma squared for the distribution on the likelihood. Here we have sigma prior. So this is sigma sub p squared is a different number than sigma. Okay, p for prior. Yes?
Why do we assume that mean is 0?
We could assume something else. You're allowed if you have other reasons for deciding your prior as a different sort of starting point. The reason a good reason to go for 0 mean is to say that the gradients phi that we're solving for should be small. If they are very large, we're assuming a very large slope to that line in all directions. So you're allowed to do that, but then you would have to say which way are they very big. So if I illustrate the prior. We'll come back to this part of the slide in a moment. This is our prior that we're assuming right now. We're saying if you just had phi 0 and phi 1, so it's a very small dimensional data, and our gradients are just 2, right? So we say phi 0, phi 1. We'll have this Gaussian, and we can center it at at 0, or we could shift it to the right and shift it up. Then you'd have to have a good reason why you think, yeah, it should be, over here at plus 5 minus 5, so at down to the right. So we have our likelihood, we have our prior, and our goal is to solve for probability of phi given x and w, right? That's this we've been talking about already, right? Probability of the part of theta we care about, so phi given x and w equals this divided by the evidence. Right. So you don't even need me here, right? You could do this already because you know this relationship, and you know this relationship because you know that this is what we care about, the joint probability of the parameters in the world state. All right. When you, we have a normal distribution on W. We have a normal distribution on phi. In chapter 5, we talked about how you can do a change of variables, right? You remember this? I think Dan Stoyanov presented this. He said, right, if you have a Gaussian distribution which is based on some linear function, and you could switch the variables around. You just have a new mean and a new variance, so you have to compute those. So in this case, you multiply this Gaussian by this Gaussian, you'll get a new mean and new variance. If you work out the math, you'll end up with a normal distribution on phi. You could have easily gone in the other direction, right? You could have made a normal distribution on W. You come up with a normal distribution on phi, which looks like this, where A is this cool matrix, right? Which includes both the sigma and the sigma on the prior. So the sigma overall for our distribution, and the sigma just on our prior for the parameters here. Now, when you compute this posterior, right? So you're computing all of Bayes' rule. We're taking this equals this over here. So you compute that whole right-hand side of the equation, given this as a prior. Then you end up with this as your posterior. It says, right, the posterior probability of some combination of phi 0 and phi 1 is very low here, very low, and it's quite high here with this sort of fall off. So this is quite representative. Whenever you have some sort of situation with the prior, and then you incorporate the prior on top of the likelihood, you end up with a tighter relationship. So it narrows the probability distribution so that it looks still not a single point, but it looks more tightly distributed. So a good reason to have this out very broad is because maybe we don't know what phi 1 and phi 0 are, but after we observe some data, pairs of the input and the outputs, we end up with this. All right, so we could, if we did maximum likelihood, the thing we just talked about a few moments ago, we were picking that point there. We were saying phi 0, phi 1, the best combination, it would be that dot in the middle of the hotspot there. But here we're saying, oh, we're going to keep track of the fact that you could have different phi 0, phi 1s. And at test time, I'm going to want to do inference. I'm going to give you an input x star. So x star as opposed to the x's that I use for training. Right? So I'm going to give you some input x star. We're going to take also our pairs of training inputs and training outputs. And I would like to compute the probability distribution on w star. What is the state of the world? The speed of the person walking, or the tilt of the head, or the splash in the pool. Right? And to do that, we're going to do this weighted sum. Now, let me come back to the weighted sum in just a moment. Let me go back just for a second. Remember, we said this is our posterior for our phi's. Phi 0, phi 1, there's this hotspot. If I sample from this space, I throw a dart and I say, okay, I landed somewhere here. That's a phi combination that I could use. I would take the strength of that, so the how hot is that, and I would apply that weight when computing the probability of my new world state. So if I take, here we have combination phi 1, like throwing the dart once. I say I'm going to incorporate x star, my new test input, and what is the distribution on w star? And it would kind of look like this. If I picked a different combination of my phi's, right? So phi combination number 2, same input, my world distribution would look a little bit different. And so you should be seeing here that you get different shapes depending on where we are in this parameter space. I mean, we knew that, right? We kind of expected that. Yeah, that's why we want to pick a good one. Or instead of picking the single best one and saying you get 100% of the vote, we could distribute the vote according to these weights and say, all right, some of these combinations are more likely than others depending on the color, the strength, the intensity of the color here. And so that's in fact how we're doing this inference. We're saying, all right, you've got this color represented here, this weight, probability of phi, given our training data. Right, so that's going to weight this term, this probability of w star given x star and our parameters. So here the parameters are fixed, but we're using this integral and over d theta to say I'm going to try sampling not once or 3 times, but infinitely many times. I'm going to sample all over the space of phi's, and every time I'm going to say, well, that weight times this probability is what I think the world state is in. It so happens that, again, that's a normal distribution on phi, right? We've already sort of established that. You should see that from our previous slide. We have a normal distribution on w star because we defined it that way in the first place, right? We're just taking x star times the weights that we computed. So you can do this in MATLAB. And when we work through it, we end up with a normal distribution on w star. So it's okay that we don't come up with a single answer. We didn't want to come up with a single answer, right? We wanted to have a distribution. But we didn't want it to matter what our parameters were. And indeed, this way, it doesn't. Our parameters, we fit them as carefully as we could. We used our prior on the parameters. But now we have this new distribution, the probability of w star given x star, and all the training data, right, is this Gaussian here, this one. And this is what it looks like. So you should see that now it's sort of more concentrated where the data is. So it is less dependent on a little bit of noise in the parameters, and data points that are far away from our training examples are now much less likely. Right? So we're not going to express with high confidence what should be happening out here. And we're still accomplishing the same regression task as before, right? Our output is some probability of w star here. Okay? So we've got our Bayesian learning of our parameters to do linear regression. A few practical issues come up. So in computing the A matrix, we might have these rather large matrices if X is high dimensional. So that doesn't seem so bad, but at some point we have to do an inversion. So here we have A inverse, and here we have A inverse. Now that can be quite costly when you have a very big matrix. So we can take advantage of something called the Woodbury or matrix inversion lemma. This is in the appendix of the book, and it gives you the formula for this. But the attractive part of it is the thing that, maybe we're definitely not going to go through it now. But the thing to note here is that previously, if you had to take the inverse of A, now when we take the inverse of A, instead of having to worry about all the d-dimensional vectors x and trying to invert them, here we're going to be inverting this thing. Now, in this thing, our x vector transpose times x. X we've erased, but what dimension was x? It was d by I. So if we take, what is this? Transpose? I by d times d by I. The output dimension is I by I. So I by I, depending on which you have more, training examples or dimensions in x, I by I might be much smaller than d by d. So that's the big selling point. It says, I don't have that many training examples, but I have a 500,000 dimensional vector describing all the pixels and all the things that are happening in my image. Do I really have to go through this inversion? And you say, no, you don't. You can use this formulation, which only has to worry about inverting a smaller I by I matrix. Equally, if you have lots of training examples and your x is small, you would look at this and say, ooh, better not use the matrix inversion lemma. That would be foolish, right? So you can take a judgment depending on your problem. All right, so when you do this matrix inversion lemma, it's this equation to impress your friends, to put in your thesis, right? And all it's doing is a slightly more intricate version of inverting a matrix. It's got its own proof behind it. Is that okay? We know why we would do this, or when? Okay. We glossed over variance. We said, you know what? Let's just in theta. Let's just worry about the phi's, the slopes, the y-intercept and the slope of our phi's. We won't worry about the variance sigma squared. So we could do this in a maximum likelihood way. So even though we might remember we have choices, right? When we're fitting the phi's, we could do this in a maximum likelihood way, which we did at the beginning of today. We could do it in the Bayesian way, which we did just a moment ago. But whichever we choose, we could come back afterwards and say, you know what? Rather than predefining a sigma for my covariance, for my variance of my normal distribution, let's fit it to the data using a maximum likelihood approach. And so the way to do that is to say, all right, I've already estimated my phi's, my phi hat, for example, or I've estimated my distribution on phi's, and therefore I know what my distribution looks like, right? It was that more concentrated dot that we introduced. And so we integrate that out, and we say, all right, when we solve for our distribution on W, we end up with this. So still, we will have to sample different, sorry, I'm pointing here. All right, we will still have to sample different phi's, sigmas. We'll still have to sample different sigmas and see which one maximizes this Gaussian. But we can just do this with a line search, sampling along until we find one that's the maximum. So in this way, it's not closed form, okay, but it's only a single scalar value, and so you can find the sigma that maximizes your overall posterior. Okay, that's it. We will continue next time with nonlinear regression, where we use something more complicated than rise and run.